Hey everybody, in this video, we're going to go over how to find the integrals of trig functions. That's one of the trickier things that you'll be asked to do when you're taking integrals. So feel free to ask any questions throughout, but otherwise I'll just kind of jump into where we left off yesterday. So if I go there, let me open these real quick. So just as a brief summary for what we talked about yesterday, let me share. So yesterday we talked about how to take the integral of polynomials, right? So we talked about the three basic rules that you need. You needed the constant multiple rule, right? Actually, that was for the previous day. The three rules we needed were the sum rule for integrals, the constant multiple rule for integrals, and the anti-power rule. And if you know those, then you could find the integral or the antiderivative, the indefinite integral of basically any polynomial. So anything like this, and also things that are a little bit more complicated than that as well. So we talked about that. And then now what we're going to do, remember, that was one of the four major functions. Polynomials is one, then trig functions, exponentials, logarithms. Today we're going to talk about the trig functions. So let's go there. So if we hop over to hop over to a new one today. Let's see. So so if we hop over to the trig functions now, let's talk about it. So and again, the same theme that we've been talking about is still applies, right? So there's like a bunch of new indefinite integrals, so to speak, right? So there's a bunch of new indefinite integrals. What we want to do is we want to we want to basically do the opposite of the rules that we already know. So first off, I'm gonna leave I'll just actually write the trig derivative rules that we already know. So the derivative of sine is cosine. So the derivative of cosine is negative sine. The derivative of secant is secant tangent. And then the derivative of tangent, or sorry, I'll say cosecant first, actually. Cosecant is equal to negative cosecant cotangent. The derivative of tangent is equal to secant squared. And then the derivative of cotangent of x will be negative cosecant squared. So hopefully that makes sense. So these are the trig derivatives, and you kind of need to know those. But after you know those, then again, integrals are really just the opposite of the rules we already know a lot of the time. So it'll be like the rules that we're going to talk about now, the integral rules for trig functions, a lot of them are going to be the same. So basically, if you just take each of these, so here's what I'll do. I'll just let me edit this. So if I just get rid of all this stuff, so if you get rid of all this, so get rid of everything on the right side. So actually, I'll get rid of that too. So get rid of everything equals like the equal sign and over. So get rid of all this stuff. If you're taking the integral of any one of these things, right? If you're taking the integral of any of these things, so the integral, and then dx, 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 dx. Basically, what that's going to be is right. The right side of all of these equations is going to end up being the left side. So the left side of what we have below. So if I come back here, I'll again, I'm kind of cheating here, so I have to do less writing. But basically, my point is that everything is the opposite now. So if I just get rid of these, so get rid of these, get rid of these, so get rid of these. It's basically, yeah, if you like whatever derivative rules you know, you just literally look at them backwards. And that's also, or actually, let me delete these, get rid of this. Trying to mass production for my drawing right now. So if we're looking at these, then these are true, right? So the antiderivative of cosine is sine. Just because the derivative of sine is cosine, the antiderivative of cosine is sine. The derivative of cosine is negative sine. Well, the antiderivative of negative sine is cosine. And by the way, what if we didn't have a negative here? Look at it like if you multiply both sides, right? If you multiply both sides by a negative, then you would get what you want there, basically. So, like, let me shrink this down a bit. Or didn't want to do that. That was definitely not good. Yeah, that was really painful. Man, I'm tempted to re-record this video from scratch. So yeah, it would have been a lot better if I just wrote it. So yeah, note to self, I'll just write it from now on. And then yeah, when you look at this, so basically all of these things, so all of these things are true with the plus C, I'll say. So if you have like, equals, so equals and then plus C for everything, plus C, plus C, plus C, plus C, plus C, equal, 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 equal. So looking at those, hopefully like this makes sense. The key idea, again, said it before, is that we're essentially doing the opposite of everything here. So all these, so the derivative of sine is cosine, the integral of cosine is sine. The derivative of cosine is negative sine, the integral of negative sine is cosine. So the same thing. So here, even though we remember like the derivative for each individual trig function on the right, you can see on the left that's actually a bit of a problem. So what do I mean by this? The issue here is actually that only two of these, and again, because like right here, what I was saying before, if you multiply both sides by a negative, you would get, right, the integral of sine is cosine. The derivative of sine is positive cosine. The integral of sine is negative cosine, what we're seeing here. So if you think about it like that, and whenever you see a negative, you can always do that trick, right? You could figure it out if there also wasn't a negative here, just by the constant multiple rule that we talked about yesterday. Pull out a negative of the integral and then multiply both sides by negative to get a different identity. So you can do that as well. But I guess the thing I want to point out is if you do that, there's only two of these. So like just from this list, just from reverse engineering the trig derivative rules that we already know, if we do that, we only really learn how to take the integral of two trig functions, sine and cosine. These are all a lot weirder, right? So like if you ever, and you will see this periodically, by the way, you will see sometimes they just ask you to find the integral of secant tangent or the integral of secant squared, and then basically the way you solve that integral is you notice that, oh, I know that the derivative of secant is secant times tangent, so the antiderivative of secant tangent has to be secant plus c. And then same thing for secant squared. So it's like you will see these, like these will come up, but these are obviously not just regular trig functions. They're like combinations of them. So that kind of begs the question, like from this, we really just know how to find the integral of sine and cosine. How do you take the integral or the antiderivative of the other trig functions? That's where things get a little harder. So that's what I'll dive into that today, just so you can get an idea, and then we'll come back to it later on. So here's how I'll think about it. Let's start off. Let's just actually ask, how would you find the integral of secant? That is surprisingly asking this question, and this is a good example of like how why integrals are so much harder than derivatives. It's actually a much easier question. What is the antiderivative of secant tangent? Like if you multiply tangent here, if you make the function we're integrating more complicated, the integral actually becomes a lot easier because then it fits a pattern we already know. The derivative of secant is secant tangent. So the integral of secant tangent is secant, as we said, secant plus c. If you don't have that tangent there, this actually becomes a significantly harder problem. And it's kind of weird too, like secant squared is a significantly easier problem if you know your trig derivatives than integrating secant. So here, how do you actually do this? I would never expect any student in a million years to come up with this idea, but you basically have to know how to do it. It turns out you can cleverly multiply by secant plus tangent, secant x plus tangent x, over secant x plus tangent x. And why can we do that? Because secant x plus tangent x over secant x plus tangent x equals 1, right? So because it's 1, it's just we're multiplying by 1, so we're not actually changing the function. Now, how would you have come up with this idea? Like I said, I never would expect a student to come up with this themselves in a million years. You have to like basically already know how to do it. But here, as we go through, you can see as we go through here, what are we going to have? We're going to have secant squared. So secant squared, if I just multiply the secant through to the numerator, secant squared of x plus tangent squared of x over secant of x plus tangent of x, right? And now another option opens up here, actually. Basically, what you can do, if I write this, so another option opens up. We can basically solve this with u sub, right? Where u is equal to the entire denominator. So secant of x plus tangent of x, right? And if that's u, what's du? Well, du dx, or if I can write it, du dx is equal to secant x tangent x, right? That's the derivative. This is where, again, you need to know your derivative rules here for trig functions. So that's the starting point to all of this. Secant x tangent of x, derivative of secant is secant x tangent x, plus the derivative of tangent x is secant squared. So secant squared. And then if you try u sub, remember we can basically rearrange this. We can say dx is equal, if I multiply both sides by dx, divide both sides by this whole thing, what do I get? I get basically 1 over this. So 1 over, I'll say, so secant 1 over that times the u. And then if I come down here, what would we do with this? Well, wherever we see dx, we're now going to replace it with this. Again, we're just doing normal techniques for u substitution here. And then think about it. For the denominator, that's what we set u equal to. We set u equal to secant of x plus tangent of x. So in the middle there, that whole thing just becomes u. And now, if you notice this, hopefully it's clear, this thing here and this thing here actually cancel out. Bang, bang. So then we get 1 over u du, like that. And this is something we can actually deal with. This is something we can actually easily integrate. What is it? Natural log of u plus c, right? Because, and this is something we haven't talked about yet, actually. This is something we will get to later. With some of the more advanced techniques. You don't really have to, like, if you already understand u substitution and how to find the integral of 1 over x, that's good. I'm just showing you the derivation. But the bottom line is you can trust this and come back later, even if you haven't gotten there yet. So think about it like this. Why do I say that 1 over u? So first off, u substitution. This is a specific integration technique, and we'll get to this later, actually. But yeah, I'll just say that. We'll get to this later. But for this, what if we have integral of 1 over u? So you can also think about it, remember, replace that u with x. Like, so what's the integral or the antiderivative of 1 over x dx? That's the question. Well, the way you answer that is, what function, if I took the derivative of it, would equal 1 over x? That's the other question to ask. And the answer to that is natural log of x, right? Derivative of natural log of x, if you know your derivative rules, is 1 over x. So that's why the integral of 1 over x, or 1 over u, is natural log of u. So hopefully that makes sense. And now what was our choice of u? Secant plus tangent. So long story short, the final answer here is natural log of secant x plus tangent x plus c. So pull this back up here. So if you're trying, actually, I'll pull this down. So what is the integral of secant of x? It's actually quite a bit more complicated than the other ones. Like, it's actually this. Natural log of secant of x plus tangent of x. Now, I won't go through the full derivation, but you could probably figure it out if you kind of copy, so to speak, the work that we did above. If you try to find an integral of cosecant of x, it's going to turn out to be negative natural log of cosecant of x plus cotangent of x plus c. And the way you get that is you actually do what looks like almost the exact same work above, except one detail is that you initially multiply by, instead of multiplying by secant plus tangent over secant plus tangent, you multiply by cosecant plus cotangent over cosecant plus cotangent. And then you do, for your u substitution, you do u as the denominator again, cosecant plus cotangent. And if you just do that and kind of do what I did here for the rest of it, take into account your trig rules, your trig derivatives will look similar but slightly different. Basically, they'll all be negative, and they'll all have the letter CO in front of them for the trig functions. Instead of secant tangent, it's cosecant cotangent, CO in front of the names. So I'll leave that to you. But if you do that, long story short, you'll get this as the answer. You'll get negative like the integral of cosecant is negative natural log cosecant x plus cotangent of x. So these are harder, right? These are not merely the opposite of the trig derivatives that we already know, because we can't really just do the opposite. Like the derivative of our trig functions never gives us just secant or just cosecant. That's why it's like the pattern. It's not easy. It's not simple. It's not as simple as just reversing the pattern, unfortunately. But that's what we would get here. So hopefully that makes sense. And then now, what I'll do for this last one here, let's do let's do a couple more. So we now know. Think about it. We now know how to take the integral of sound like a broken record there. Sine, cosine, secant, cosecant. Which two do we not know yet? Cosecant and cotangent. So let me show those. So if we do that, let's walk through those. How would you find the integral of tangent? This one is actually, I think, a little bit easier than what we did above. It's not quite as out of left field. Like the thing we did up here, like I said, I mentioned this already, but multiplying by secant of x plus tangent of x over secant of x plus tangent of x, I would never expect a student to come up with that idea in a million years. I wouldn't have come up with it myself in a million years. But somebody in human history did, and now we know about it. So that's the way to figure that out. With this one, I actually can see a student, and even myself, coming up with this idea. How would we do this? We can't just directly use the rules in reverse. The trick is actually to write it like this. Remember, tangent is always sine over cosine. And when we look at it like this, now we open ourselves up for another use of u is equal to cosine of x, du dx is equal to negative sine of x, right? Which would imply that dx is equal to 1 over negative sine of x du. And now we can do the substitution, no problem, right? So sine, leave that, sine of x, cosine, replace that with u. And then dx, replace that with 1 over negative sine of x du. And if you think about it, what would happen here? The sine x cancel out. So now what do we get? We basically get negative. You can pull the negative out, and you should pull the negative out. Negative integral 1 over u du. So negative integral 1 over u du. We just kind of talked about this below. What is this? This would be negative natural log of u plus c. And then what was our original choice of u? Cosine. So negative natural log of cosine of x plus c. That would be our final answer. And here we can actually simplify it a little bit more if you know logarithm properties. So think about it like this. And again, this is fine, but you might see it in a different form. So that's why I just want to make sure you're aware of that. If you use logarithm properties, you can actually turn this into cosine x to the negative 1 power, right? To the negative 1 power plus c. And then what is cosine of x to the negative 1 power? You got to be careful with this notation. I am not talking about inverse cosine. That's why like inverse cosine is sometimes written like that, or like arctangent or arc cosine. I always like to use arc cosine. I kind of hate that notation for this reason, because it looks like cosine reciprocal. That's what we're really talking about. We're not talking about inverse cosine. We're talking about 1 divided by cosine. Those are different. So again, I won't get on my high horse here complaining about notation, but cosine inverse, like cosine to the negative 1 power, again, like this negative 1, there's a logarithm property that allows us to do that. So it's like usually we use it the other way. Like if you have like logarithm of something to a certain power, you can pull that power out front and get rid of it here. We're actually doing the opposite. We're like taking it from out front and putting it back in, which is unusual, but you can see why we would do that. So this thing is actually 1 over cosine on the inside. And then what is 1 over cosine? Well, that's secant. So final answer, natural log of secant plus c. So we're trying to find the integral of tangent. That would equal natural log of secant plus c. So natural log of secant plus c, like that. So hopefully, like I said, hopefully that makes sense. And then now you can kind of do it to find like the integral of cotangent. You can do something very similar. So cotangent of x, how would we do that? We would have the integral of, that's not sine over cosine, but cosine over sine, right? And then if we did this opens itself up to another u sub, right? So just u equals sine du dx cosine dx equals 1 over cosine du. And then we have integral of cosine of x over our sine is now going to become u. And then the dx is going to be 1 over cosine dx. And then if we cancel these out, cosine of x and cosine x, what do we get? We get 1 over u, or sorry, that should be du, not dx. My mistake. So let me simplify that. So that should be d du. So now this becomes 1 over u du, positive, not negative. And then what is that? Natural log, positive natural log of u plus c. Remember what u was? Natural log of sine plus c. It's actually a little bit simpler than the last case. So the antiderivative of cotangent is actually natural log of sine. So the antiderivative of cotangent is actually equal to, or sorry, this is a tiny mistake. The c should be on the outside. There. So natural log of sine of x plus c on the outside. There you go. So natural log of sine of x plus c on the outside. So that's what we get. And then putting these all together. So now let me consolidate everything that we've talked about here. So if I pull these down, so let me pull these down to start. So pull these down, and then let me get rid of some things. So let's get rid of these plus c's, and then let's get rid of all this stuff. So all that, so all that, all that, and then so all that, and then let's also get rid of all of these. So, oops. So get rid of that, get rid of that, get rid of that, that. Actually, I went too far. Keep that. Cool. And then get rid of that. We're just consolidating everything here. And here, if you think about it, you can do the trick I mentioned before. If you take this negative sign, you can pull that to the outside here, and then just multiply, because we want to find out what the integral of positive sine is. That's kind of the idea. We want to find the integral of all the trig functions. So just pull it on the outside and multiply both sides by a negative. So long story short, you would just get a negative there. So hopefully that logic makes sense. So we get that. And then, so those are two of them. So we know that the integral of cosine is sine plus c, sine of x plus c. The integral of sine of x is negative cosine of x plus c. And then we figured out the rest of these, actually. So we figured out these two. Let me pull these down. So we figured these out. I'll crop them down quite a bit. So yeah, looking at it kind of like that. And then let me get rid of the outside. Cool. There you go. So now we have the integrals of secant and cosecant. And we also have the last two, the integral of tangent. It's right there. And then the integral of cotangent is right there. So there you go. And then I'll simplify these down a bit. Let me do that. So if I bring this down, or I don't know why it's not letting me. So simplify that. And there you go. Bring it down to that size. Simplify that. Bring it down. I don't know why it's not letting me decrease the size anymore. Anyway, pretend I decreased the size. These are your integral rules for the trig functions. And you can see they're quite a bit more complex. It's not quite as simple as just taking the rules we already know and flipping them around. It's a little trickier now. So, but these are the rules. This is how you take the antiderivative. Again, it's pretty rare, to be honest, to take the antiderivative of secant and cosecant and tangent and cotangent. It's pretty rare, but it happens a lot. And then one other thing I'll mention, you can do that trick we did before here. You can like do one over that, right? If you pull the negative power inside, then one over this whole thing. You might see that as well, but I'll just leave it in that format. So these are the integrals of your trig functions. And by the way, if you're skeptical of any of those, remember you can test these all out, right? So these first two are easy, right? You just take the thing on the right. If you take the derivative of it, is it the thing on the left? And the answer is yes, actually. And then if you take the derivative of negative cosine, well, what's the derivative of cosine? Negative sine. So negative sine is positive sine. So that checks out too. And then here, if you take the derivative of natural log of secant x plus tangent of x, actually, I'll probably do this below here. So if you take the derivative of this, or maybe I'll move to the right. Well, what would that be? You have to think of it like the chain rule. So if you do the chain rule in your head, derivative of the outer function is 1 over x, but it's not x. You just leave the inner function, right? And then you can see how this is going to go. You basically take the derivative of the inner function, which is secant tangent plus secant squared. So secant tangent, secant x, tan x. You basically do everything we did in reverse, plus secant squared. And then you can pull out a secant of both of these, and then the secant x plus tangent of x cancel out. And yeah, you are left with secant. That works out. If you try the second one, it's very similar. Natural log, or I'll say negative natural log of uh yeah, cosecant x plus cotangent of x. It's actually I'll leave you to do this, but it's essentially the same process above. So negative 1 over cosecant plus cotangent, then the derivative of that is negative cosecant squared, negative cosecant cotangent plus or minus or plus negative, I'll say cosecant squared. Then you can factor out a negative. The two negatives outside cancel. The cosecant plus cotangent, after you factor out one cosecant, you're left with cosecant plus cotangent in the numerator and the denominator. That cancels, and you'll just be left with cosecant. It's almost the exact identical thing to here. And then with these last two, these are slightly different. So here, if you take the derivative of natural log of secant, 1 over something, what's something, secant, times the derivative of the inside, secant tangent. Secants cancel out to give you just tangent. That checks out. And then finally, this last one, natural log of sine of x. If you take the derivative of that, what do you get? You get 1 over sine, right? 1 over x for the derivative of the outer function evaluated the inside. We're doing the chain rule in our heads here, basically. And then what's the derivative of sine? Cosine. Cosine over sine is literally cotangent. That's literally what it means. Voila. So hopefully that idea makes sense. So this, you can see that like what we found is correct if you just take the derivatives to check them. But if you want to remember the integral rules, honestly, I wouldn't. If you wanted to prioritize it, I would definitely know how to do the first two. And I would actually, these, you can think about the trig derivatives backwards. These other ones are far more complex. Honestly, if you had, like I said, unless you're in a very difficult class, this is unlikely to come up. But if it does come up, then you will want to remember these. But to be honest, in most classes that I see, you can get by without remembering these last four here. But if you need them for your class and you want to remember them on the test to move faster, this is how you do it. Hope that helps. If anybody has any questions, like I said, feel free to just post in the Skool community, and I'll answer them. But otherwise, hope that helps, and I will catch you guys tomorrow. See ya.